In this example for section 15.1, we wanted to determine if f is conservative. If so, find the potential function. Again, recall that the vector field f is in bold, and I use that vector notation here. F is equal to mi plus nj. Our test to determine if a vector field is conservative is if the partial of m with respect to y is equal to the partial of n with respect to x, then we could say f is conservative. So let's go ahead and find those, letting m equal e to the y plus 2x. We want to take the partial derivative of m with respect to y, treating y as a variable and x as a constant, and that partial derivative is e to the y. Let n equal x e to the y minus 1. We want to take the partial derivative of n with respect to x, treating x as a variable, y as a constant. So x times this constant is the constant, which is e to the y. Now these are the same, so we can say yes, these are equal. So f is conservative. And if it is conservative, then we can find a potential function. Okay, if it is, let's find the potential function. The way we find the potential function is by integrating m with respect to x and integrating n with respect to y. And we're going to combine those to find our potential function f of x, y. Let's integrate e to the y plus 2x dx, treating x as a variable, y as a constant. So that is going to be the antiderivative of this constant is a constant times x. So we're treating e to the y as a constant. So e to the y times x. And the antiderivative of 2x with respect to x is x squared. Plus, we could be adding constants here, but instead of just adding a plus c, we treat y as a constant, so we could have y's in this as well. So we write this as plus g of y, which means it's a function of constants where we could also have a y. Let's look at the antiderivative of n with respect to y. That is antiderivative of x e to the y minus 1 dy. Treating y as a variable, x as a constant, the antiderivative of e to the y is e to the y times that constant, which is x times e to the y. The antiderivative of minus 1 with respect to y is minus y. And then plus we could have constants here or x's, so we're going to add h of x. So this is like our adding our plus c here when we do antiderivatives, but we're treating y's and x's as constants in these. So the potential function is found by combining these. We have notice that they both have this common term of x e to the y. We only put it one time in our potential function, x e to the y. Now we also want to include this plus x squared. We don't see that in the other one, but that is actually part of this constant that we added here. So our potential function is equal to this, and it's equal to this, but we're treating those as constants when we added that. So we have a plus x squared that's included in our potential function. And over here we have a minus y that's also included. We don't see it in the first antiderivative because in that case we treated y as a constant. So that's kind of taken care of by adding that. And then there could be some other constants, true constants, plus c. So this is the potential function. The potential function of the vector field f of x, y. And again, what that means when you find the potential function, that means that if you took the gradient of that f of xy, you would get a vector field, and that vector field would be that f of xy that we started off with. So we say that this vector field is conservative, and it's conservative because it is the gradient of this potential function f of xy.